Faraday's Law 3. Through the loop shown, suppose the magnetic field varies with time according to this equation. We want to derive expressions as functions of time for the induced EMF and the induced current in this loop. Clearly, this loop must be a metal. We're assuming it's a metal. If it wants to know what the induced current is, if the loop is an insulator, the induced current is going to be 0 with time. We're assuming here that the loop is going to be metal. You can see it's got a certain radius. It has a certain resistance. What we're going to find is we're just going to find the magnitude of the EMF and the magnitude of the current. What this equation means with magnetic field, you know that the cosine ranges from +1 to -1. And so what would that mean with regard to the magnetic field if, as time goes on, the magnetic field is, in a sense, becoming negative, or it's becoming positive, and then negative again, and then positive? It just means that the direction of the field is changing. At some times, the magnetic field is pointing out of the page at us through this loop, and then at other times it's pointing into the page, and then a little bit later it's pointing out, and then it's pointing in. That's going to cause the direction of the EMF around this loop. Sometimes it'll be clockwise, then it'll turn to counter, then clockwise, then counterclockwise, and so on. Same thing for the current. We're just going to find the magnitudes here. So how do we do this? Faraday's law says that the induced EMF is numerically equal to, and I'll put absolute value signs since we don't want to put the negative sign. We will learn about that negative sign here. It's related to something called Lenz's law, which we'll meet in upcoming videos. But we want to take the time derivative of the flux, and we remember that the simple explanation for flux is essentially the magnetic field multiplied by the area through which the field is traveling. The A here is constant, and so I can kind of pull that outside, and then by the magic of calculus we can rewrite the rest of this to look like so, which allows us to say, you know what, I think we just need to take the time derivative of this magnetic field expression. Let's go ahead and do that. Let's write the area down first, since that's real easy. The area is going to be pi r squared. We're going to want to change that into meters, so I've done that, and then I'm going to be a little bit lazy. I'm not going to put the unit there, but I know it's right now. So that's the area. I'll go ahead and label that. There's the area. Now let's differentiate this magnetic field equation, and whenever we differentiate, we've got that constant of 26, which we're just going to rewrite. Then when we take the derivative of cosine, we get the negative sign. We're not worried about positives and negatives here, so I'm just going to write sine of 3 pi t. And then whenever you take a derivative of a sine or a cosine, you have to use the chain rule, which means we need to then take the time derivative of this thing in parentheses. So there's going to be another factor of 3 pi on the outside there. Hopefully you're okay with what's just happened here. We've got the area, and then here, right there, is our dB dt. And it looks like we're just going to have to crunch a number here with our calculator. And when I did that with our calculator, I got about 11.1 for all of this stuff. Pi 0.12 squared, 26, 3, another factor of pi. I got about 11.1 times the sine of 3 pi t. That is the magnitude of the EMF that's induced due to this changing magnetic field. What about the current? That's real easy, isn't it? Because by Ohm's law, the current is just going to be the voltage, which is right here, divided by the resistance. The resistance of this coil is given as 2. The magnitude of the current at any particular time, maybe I should stick that in there as well. Should I put a little T in here for this is the EMF at any particular time, is just going to be all of this divided by 2. Well, 11 0.1 divided by 2 is 5.55 or so times the sine of 3 pi t.